Welcome to your quiet corner of cosmic discovery. I'm here to share something genuinely fascinating about our universe at just the right volume for drifting off. You know, I've been thinking about how the tiniest particles inside atoms hold such incredible power that can both light up cities and warm our homes. There's something remarkable about how splitting or even joining these tiny pieces can release energy in ways that feel almost magical, yet it's all grounded in the quiet, precise dance of nature. I'm excited to share with you the gentle secrets behind this amazing process and why understanding it feels like unlocking a special kind of wonder. Your gentle engagement through likes and subscriptions illuminates this quiet corner of knowledge. Let me know in the comments what scientific mysteries you'd love to explore together. Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. Beneath the surface of all things, beneath the warmth of your blanket, beneath the firmness of your bed, beneath the quiet hush of the night's shadows, there lies a ceaseless commotion. It is a realm hidden from our senses, a theatre of unending movement and transformation, where the very foundation of matter is cast into a perpetual, invisible ballet. In this deep and secret world, the atoms dance. To understand nuclear energy, one must first learn to imagine the unseen. The word atom itself conjures images of tiny spheres, perhaps orbiting each other like miniature solar systems. Yet even this is only a pale metaphor, a shadow of the true complexity within. Each atom is a puzzle, a nucleus of protons and neutrons at its heart, orbited by a whir of electrons, all bound together by forces as powerful as they are mysterious. It is within these minute citadels, these nuclei, that the story of nuclear energy unfolds. Let us begin with the nucleus, for it is here that the heart of nuclear energy beats. The nucleus is so small, if an atom were the size of a cathedral, the nucleus would be no more than a single grain of rice at its center. And yet, it is here that most of the atom's mass resides, locked in a close embrace between protons and neutrons. These particles are themselves made of even smaller quarks, bound by the strong nuclear force, a fundamental force of nature that dwarfs gravity, that binds the universe's very fabric at short distances. The strong force is a paradox, immense in strength, but limited in reach. It is this force that holds the nucleus together, overcoming the electric repulsion that would otherwise fling the positively charged protons apart. And yet this same force, so mighty and so short-lived, provides both the stability and the instability that underlie the phenomenon of nuclear energy. For in certain arrangements, the nucleus is stable, content to persist for eons. In others, it teeters on the edge of transformation, yearning to change, to shed mass, to release energy in a sudden, cataclysmic flourish. It is in these moments, when the nucleus splits or when smaller nuclei fuse, that nuclear energy is born. But before we proceed into the depths of nuclear alchemy, let us pause and listen to the echoes that drift down to us from the halls of culture, from the stories and fears and dreams that nuclear energy has inspired. For this energy, so firmly rooted in the physics of the tiny, has cast a shadow far larger than its size would suggest. Nuclear energy is not only a technical marvel, it is a symbol, a spectre, and at times a promise. In the early decades of the 20th century, as physicists first pried open the nucleus and glimpsed the energies within, the world trembled on the brink of transformation. The discovery of radioactivity by Becquerel, the isolation of radium by the Curies, the deciphering of the atom structure by Rutherford, all these found their way into the imagination of poets and politicians alike. The atom, once thought indivisible, was revealed to be a hive of activity, a source of power so vast that it seemed almost godlike. Science fiction, always alert to the tremors of discovery, seized upon the atom's potential. Early stories dreamed of atom-powered cities, of ships that could sail forever without fuel, of utopias in which energy was infinite and free. The atom was Prometheus's fire, recast for the modern age. But alongside these dreams grew darker visions, tales of atomic monsters, of worlds laid waste by radiation, of cities annihilated in an instant flash. The splitting of the atom and the birth of the atomic bomb in the fires of World War II seared itself into the collective consciousness. Nuclear energy became twin-faced, at once a promise of abundance and a harbinger of destruction. These cultural associations linger still, shaping how we speak and think about the atom. Even the word nuclear is weighted, heavy with both hope and dread. News stories speak of nuclear disasters, of meltdowns, of fallout drifting on the wind. Films show glowing symbols, ticking countdowns, and the haunting silhouette of the mushroom cloud. And yet, in quieter corners, scientists and engineers speak of nuclear reactors humming gently, of isotopes that heal, of the power of the stars brought safely to Earth. Much of the public's sense of nuclear energy is, in truth, shaped less by physics and more by myth. There is a tendency to conflate all things nuclear with the bomb, to imagine that reactors and weapons are but two sides of the same coin. There is a fear that nuclear power is inherently unmanageable, that radiation is an invisible poison, that all things atomic are best left untouched. These fears are not groundless. Nuclear energy does carry risks, and its history is marked by moments of tragedy. But the reality is subtler, more nuanced, and in many ways more wondrous. To separate fact from fiction, let us look more closely at what nuclear energy truly is. At its core, it is the energy released when the nucleus of an atom is altered, either split in two, as in fission, or fused together with another nucleus, as in fusion. This is not the same as the energy released in chemical reactions, such as the burning of wood or the metabolism of food. Chemical energy is the rearrangement of electrons around nuclei. Nuclear energy is the rearrangement of the nuclei themselves. The energies involved are of a different order, millions of times greater per reaction, enough to power cities or to obliterate them. Perhaps the most common misconception is that nuclear energy is, in and of itself, a source of uncontrollable danger. The word radiation often evokes images of glowing green goo, of mutations and sickness, of landscapes rendered uninhabitable for centuries. But radiation is not a single thing, nor is it always deadly. In fact, the world is awash in radiation, in forms both natural and benign. The warmth you feel from the sun on your skin is a form of electromagnetic radiation. The potassium in your bananas emits tiny, harmless bursts of radioactivity. Cosmic rays from distant galaxies rain down upon the Earth, passing invisibly through our bodies every second. The radiation associated with nuclear energy is primarily the result of unstable nuclei seeking stability, emitting particles or rays as they transform. Alpha particles, heavy and slow, can be stopped by a sheet of paper or the surface of your skin. Beta particles are more penetrating, but still easily shielded. Gamma rays are more energetic, but even these can be blocked by thick walls of concrete or lead. The danger of radiation lies not in its mere presence, but in its intensity and in how it is managed. Nuclear reactors, for example, are designed with layers of shielding and safety systems. The fuel is contained within robust vessels. Control rods regulate the chain reaction. The entire process is engineered to harness the energy of the atom in a controlled, sustained manner. When things go wrong, as in the rare but infamous cases of Chernobyl or Fukushima, it is often a failure of systems, technical, human, or both, rather than an inherent malevolence of the atom itself. Another common misconception is that all nuclear waste is unimaginably dangerous, destined to plague the Earth for millennia. In reality, Most nuclear waste is low-level, consisting of lightly contaminated tools or clothing. The high-level waste, primarily spent fuel rods, is indeed highly radioactive and must be managed with care. But its volume is small compared to the waste produced by fossil fuel industries, and it is meticulously tracked and stored. The challenge of waste disposal is real, but it is not insurmountable, nor is it unique to nuclear power. The notion that nuclear energy is uniquely susceptible to catastrophic accidents also bears scrutiny. While the consequences of a major reactor failure can be severe, the frequency of such events is exceedingly low. By contrast, the slow, invisible toll of air pollution from coal and oil claims millions of lives each year, a statistic rarely ascribed the same urgency. The visible, dramatic failures of nuclear power loom large in memory, but the steady, everyday harms of other energy sources are often overlooked. There is a further misconception, deeply rooted in the cultural imagination, that nuclear power is obsolete, a relic of the Cold War, supplanted by newer, cleaner technologies. While it is true that wind and solar have grown rapidly in recent years, nuclear energy remains one of the few sources capable of delivering large amounts of electricity with minimal carbon emissions. In a world grappling with the challenges of climate change, the atom's promise persists quietly and stubbornly in the background. And then there is fusion, the holy grail, the dream that has danced on the horizon for generations. Fusion is the process that powers the stars, the merging of light nuclei into heavier ones, releasing prodigious energy in the process. Unlike fission, which splits heavy atoms, fusion joins light ones. It offers the tantalizing prospect of limitless, clean energy, with fuel drawn from the oceans and waste that is far less troublesome. Yet for all its promise, controlled fusion has remained elusive, a riddle yet to be solved. Scientists continue to pursue it, building ever more ingenious machines, seeking to replicate in the laboratory what the sun accomplishes with seeming ease. As we drift through these layers of understanding, from the nucleus to the reactor, from myth to reality, a more nuanced picture of nuclear energy begins to emerge. It is neither savior nor monster, but a tool, a profoundly powerful one to be sure, but a tool nonetheless. Its dangers are real, but so too are its benefits. Its mysteries are deep, but not impenetrable. Consider for a moment the smallest act of transformation within the nucleus, the emission of a single alpha particle, the fission of a uranium atom, the fusion of two hydrogen nuclei. Each of these is a dance, a rearrangement of matter and energy at the most fundamental level. The energies released are the echoes of forces that shaped the universe itself, the forging of the elements in the hearts of dying stars, the lingering glow of radioactive decay that warms the Earth's interior, the brilliance of the sun that sustains all life. The atoms themselves are indifferent to our hopes and fears, to our stories of doom or utopia. They follow the rules of physics with relentless precision, their dance unceasing, their energies vast and ancient. It is we, the observers, who must choose how to direct their power, how to balance risk and reward, how to see past the myths into the heart of the matter. In the quiet of the night, as you rest, the dance of the atoms continues, unseen but unceasing. The story of nuclear energy is far from over. It is a prelude, a first note in a symphony that stretches from the birth of the universe to the dreams of the future. And as the curtain rises on this atomic ballet, we are left with questions about the nature of matter, about the promises and perils of power, about the ways in which human ingenuity and imagination might yet shape the energy of the stars. In the stillness, one might wonder, what is it truly that holds the nucleus together? What forces are at play in those minuscule halls, and how do they give rise to both the quiet glow of a reactor and the explosive force of a bomb? These are questions for another act, another movement in our exploration as we descend deeper into the heart of the atom, seeking the secrets that lie within. Deep within the layered architecture of matter, beyond the silvery flicker of electrons and the empty spaces that seem to make up most of the atom, there lies a denser, stranger realm, the atomic nucleus. It is here, in this infinitesimal heart, that nature's most potent energies are both concealed and unleashed. For all the atom's apparent simplicity, a nucleus orbited by electrons, a miniature solar system of sorts, it is within this nucleus that the true drama unfolds, a spiraling mystery that has beckoned scientists for generations. Consider for a moment the scale of things. If an atom were the size of a cathedral, its nucleus would be a grain of rice suspended at the very center, while the electrons would be like motes of dust whirling in the distant aisles. Yet almost all the atom's mass, its weight and substance, is packed into that tiny grain. Inside it, protons and neutrons are bound together by forces whose nature is both familiar and utterly alien. They are not held together by the magnetism that guides a compass, nor by the gravity that anchors us to the earth, but by something still more primal, the strong nuclear force. This force, the most powerful in the known universe at subatomic distances, is both the glue and the paradox of the nucleus. It draws protons and neutrons into a tightly knit cluster, overcoming the natural repulsion between the positively charged protons, who would otherwise explode apart with electric fury. But the strong force is capricious. It is intensely attractive at very short ranges, yet becomes negligible beyond the confines of the nucleus, leaving the protons' mutual repulsion unchecked if they stray too far. The nucleus, then, is a place of delicate balances, a dance of attraction and repulsion, of stability and potential chaos. Within this crucible, two extraordinary processes can occur, each unlocking the fierce energies bottled up in the heart of matter. The first is fission, the splitting of a heavy nucleus. The second is fusion, the merging of light nuclei. These are not just scientific curiosities, they are the beating heart of stars and the engines of our own attempts to harness the atom's power, for peace and for destruction alike. Let us drift first into the realm of fission. Picture in your mind a nucleus of uranium-235, a rare isotope nestled among the more common uranium-238 atoms of the Earth's crust. This nucleus is large, crowded with 92 protons and 143 neutrons, and precariously held together. It is stable enough to endure for millions of years, but not so stable that it cannot be persuaded to unravel. When a free neutron, itself a ghostly wisp of matter, happens by and collides with the uranium-235 nucleus, the structure shudders, absorbs the newcomer, and becomes even more unstable. The nucleus elongates, quivers, and, almost in slow motion, tears itself in two. The aftermath is astonishing. The uranium splits into two smaller nuclei, each itself a new element, and in the process releases a few neutrons and an immense burst of energy. Where does this energy come from? Here we encounter one of nature's deepest secrets. The mass of the resulting fragments is slightly less than the mass of the original nucleus and the captured neutron. The missing mass has not vanished. It has been transformed via Einstein's famous equation EXmc2 into pure energy. Because the speed of light squared is such a vast number, even a tiny loss of mass translates into an enormous outpouring of energy. This is the source of the heat that boils water in nuclear reactors, the flash that lights up the night in atomic tests, the awe and the terror of the nuclear age. Yet the story does not end with a single split. The released neutrons, set free from the original nucleus, may themselves encounter other uranium-235 atoms, triggering further fissions. If conditions are right, If there is enough fissile material, and if the neutrons are not absorbed or lost, a self-sustaining chain reaction can unfold. This is the principle behind both the controlled burning of fuel in a power plant and the uncontrolled detonation of a bomb. The difference lies in geometry, in moderation, in the careful arrangement of matter and the insertion of control rods to absorb excess neutrons. The science is subtle, but the consequences are stark. Fission, for all its power, is but one chapter in the nucleus's story. Fusion, its mirror image, is at once more elusive and more fundamental. It is the process that lights the stars, that forges the elements, that makes life possible. In the core of the sun, where temperatures soar to millions of degrees and pressures are immense, hydrogen nuclei, mere protons, are forced so close together that the strong nuclear force can overcome their mutual repulsion. When two protons fuse, they form a deuteron, a nucleus of deuterium, a heavy isotope of hydrogen, releasing a positron and a neutrino in the process. Through a series of such steps, hydrogen is transmuted into helium, and with each reaction, energy is released, radiating outward to warm the planets and the cold void beyond. Fusion is, in a sense, the opposite of fission. Whereas fission splits heavy nuclei into lighter ones, fusion joins light nuclei into heavier ones. In both cases, the products are more tightly bound than the reactants, and the difference in binding energy is liberated as heat and light. But the conditions required for fusion are far more extreme. On Earth, achieving the temperatures and densities needed to coax nuclei into merging is a monumental challenge. For decades, scientists have sought to recreate the sun's fire in laboratories, using magnetic fields to confine seething plasmas or aiming lasers at tiny pellets of fuel. The promise is vast, a virtually limitless source of clean energy, with no long-lived radioactive waste and no risk of runaway chain reactions. Yet the technical hurdles remain formidable, and the dream of practical fusion power hovers tantalizingly on the horizon just out of reach. There is a curious symmetry here, a kind of cosmic poetry. The heaviest elements, like uranium and plutonium, are prone to fission because their nuclei are so large and unwieldy, their protons straining to escape the mutual embrace. The lightest elements, like hydrogen and helium, are the fuel for fusion because their nuclei are small, their binding energies low, and their fusion yields a deeper, more stable union. In the middle, elements like iron and nickel are the most tightly bound of all, their nuclei so stable that neither fission nor fusion can extract further energy from them. In a sense, the universe is always striving for stability, for the lowest energy state, and the processes of fission and fusion are the means by which it moves toward that goal. Yet, as we probe deeper into the nucleus, we find that our understanding is still ringed with mystery. The strong force, for all its power, is not fully tamed by our equations. It is described by quantum chromodynamics, a theory of quarks and gluons, but the mathematics is fiendishly complex, and many puzzles remain. The neutron, for instance, is stable inside the nucleus, but when free, it decays in a matter of minutes, transforming into a proton, an electron, and an antineutrino. Why should this be? Why do some nuclei last for billions of years, while others shatter in an instant? The rules are subtle, encoded in the interplay of forces and the quantum symmetries that guide the subatomic world. Even the nature of radioactive decay, the spontaneous transformation of one element into another, remains a realm of surprises. In alpha decay, a nucleus spits out a cluster of 2 protons and 2 neutrons, a miniature helium nucleus, tunneling through the energy barrier that surrounds it. In beta decay, a neutron transmutes into a proton, emitting an electron and a ghostly neutrino. Each decay is a roll of the cosmic dice, unpredictable in the fate of a single atom, but utterly reliable in the aggregate, a testament to the strange regularity of quantum events. Our attempts to harness nuclear energy, whether through fission or the quest for fusion, are a testament to both our ingenuity and our humility before nature's power. In the early days of the atomic age, some dreamed that nuclear power would usher in an era of abundance, with electricity too cheap to meter. Others feared the shadow of destruction, the mushroom cloud that could erase a city in a single flash. In the decades since, we have learned both caution and awe. Nuclear reactors now provide a significant fraction of the world's electricity, their steady hum a background to modern life, while the waste they produce poses questions that will echo for centuries. Fusion, still just a promise, invites us to imagine a future where the energy of the stars is ours to command, yet always just beyond the grasp of our machines. But amid these grand ambitions, we must also contend with the limits of our knowledge. The nucleus is not a static thing. It is a seething, dynamic assembly, its constituents governed by the probabilistic laws of quantum mechanics. The very forces that bind protons and neutrons together are mediated by particles called gluons, whose interactions are so complex that even the world's most powerful supercomputers struggle to simulate them. The magic numbers of nuclear physics, those numbers of protons and neutrons that confer extra stability, hint at deeper symmetries, patterns woven into the fabric of the atomic world that we are only beginning to unravel. And then there are the exotic nuclei, the isotopes created in the crucibles of supernovae or in the laboratories of particle physicists. These are nuclei far from stability, with strange ratios of protons to neutrons, living for fractions of a second before decaying into something more familiar. Some may exist only fleetingly, yet they play a crucial role in the cosmic alchemy that builds the elements. The calcium in your bones, the iron in your blood, the gold in a wedding ring, all were forged in the hearts of ancient stars, assembled by the processes of fission and fusion carried across the cosmos in the aftermath of stellar explosions. There are, too, the mysteries that lie at the boundaries of our knowledge, the questions that remain unanswered, the phenomena that defy our current theories. What, for example, is the true nature of the neutrino, that near-massless particle produced in beta decay? Why do some isotopes undergo double beta decay, emitting 2 electrons and 2 neutrinos, while others do not? What lies beyond the standard model of particle physics, whose symmetries and particles seem so elegant and yet perhaps incomplete? The nucleus is not merely a repository of energy. It is a gateway to the deepest questions of existence, a place where the known and the unknown meet in a dance of possibility. As we contemplate these mysteries, this spiraling heart of the atom, this forge of creation and destruction, we find ourselves at once humbled and uplifted. The nucleus, so small as to be invisible even to the finest microscopes, contains within it the forces that shape worlds and the puzzles that challenge our finest minds. Our journey into its depths has brought us both light and shadow, both wisdom and the awareness of how much remains to be learned. And so, as night settles and the world grows quiet, we linger in the half-light of understanding, our imaginations circling the heart of the atom, pondering the energies we have glimpsed and the secrets still concealed. In the next phase of our exploration, we might turn outward once more, tracing the ways in which these nuclear processes ripple through the cosmos, shaping the stars, the galaxies, and the very elements from which we are made. But for now, let us rest in the presence of wonder, content to dwell for a while in the heart of the atom, where energy and enigma intertwine, and where each answer gives rise to new and deeper questions. To peer into the heart of the atom is to gaze through a window both ancient and perpetually new, a looking glass that does not merely show, but transforms the very fabric of the world it reveals. The journey into the atomic age was neither swift nor accidental. It was the cumulative work of generations, each step demanding cleverness, courage, and a special kind of humility before the unknown. As we drift deeper into this narrative, Let us walk the paths of those who first dared to lift the veil and trace the ingenious tools and experiments that allowed humanity to cradle the atom's secret fire in its hands. Long before the language of protons, neutrons, and electrons was spoken, the ancient Greeks had speculated that all matter was composed of indivisible units. Atomos, they called them, meaning uncuttable. For centuries, these musings remained in the realm of philosophy, untethered by experiment or observation. It was not until the 19th century, when the slow burn of the scientific revolution reached a critical mass, that atoms began to shift from abstract idea to tangible reality. The first true glimpses beneath the visible world came not through glass, but through the careful measurement of matter itself. John Dalton, an English schoolteacher, noticed that chemical substances combined in fixed ratios by weight, a quiet but inexorable clue that matter was granular, not continuous. Dalton's atomic theory, published in the early 1800s, provided the first map, albeit a vague one, for the territory of the invisible. But to truly see, one needs more than theory. One needs a tool, a looking glass to focus and reveal. In the late 19th century, such a tool arrived, not as a lens, but as a tube, a curious glass vessel, emptied of air and strung with metal electrodes. These were the cathode ray tubes, elegant and mysterious. Scientists passed electric currents through them and were astonished to see ghostly green glows dancing across the glass. What were these rays, so defiant of the familiar rules of light and shadow? It was the meticulous work of J. Thomson in 1897 that would answer this question, and in doing so would shatter the ancient notion of the atom as indivisible. Using a cathode ray tube, Thomson saw how a beam of invisible particles could be bent by electric and magnetic fields. By measuring how much the rays curved, he deduced the mass and charge of these particles. They were not atoms, but smaller still, electrons, the first of the atom's inner children to be revealed. The cathode ray tube, with its cold glass and shimmering phosphorescence, was among the first tools to show that the atom was not a solid sphere, but a miniature solar system riddled with inner structure. Yet even as electrons were discovered, the atom's core remained hidden, a dark and heavy secret. At the dawn of the 20th century, another kind of looking glass emerged, one that would not just reveal, but probe and challenge. Ernest Rutherford, a physicist of quiet intensity, devised an experiment as precise as it was poetic. At the University of Manchester, in a small laboratory thick with the scent of chemicals and the hum of anticipation, Rutherford and his assistants, Hans Geiger and Ernest Marsden, prepared a wafer-thin sheet of gold. They bombarded it with alpha particles, the heavy, positively charged fragments spat out by radioactive decay. To detect the passage of these particles, they surrounded the gold foil with a screen coated in zinc sulfide, a substance that sparkled with tiny flashes of light whenever struck by an alpha particle. Peering through microscopes in the dimness, the experimenters counted these scintillations one by one, night after night. What they found was astonishing. Most alpha particles passed straight through the foil, but a few bounced back, as if they had struck something immensely dense and compact. Rutherford's mind leapt to the only possible conclusion. The atom was mostly empty space, its mass concentrated in a tiny, positively charged nucleus at the center. The gold foil experiment had, in effect, fired bullets at tissue paper and found that, occasionally, the bullets ricocheted from something hard and massive. The nucleus had been glimpsed, if only by inference and imagination. With each experiment, the tools of the atomic age became ever more refined, and the questions more subtle. How were these nuclei bound together? What forces prevented them from flying apart, given the fierce repulsion of their positive charges? To probe further, physicists needed more than simple detectors. They needed machines that could hurl particles at atoms with ever greater energy. Thus dawned the era of the particle accelerator, a modern-day catapult for the atomic realm. The earliest accelerators were little more than glorified vacuum tubes, but they grew rapidly in scale and sophistication. Ernest Lawrence, working in California during the 1930s, devised the cyclotron, a compact spiral track in which particles could be sped up by oscillating electric fields and bent into circles by magnetic fields. In this device, protons could be accelerated to energies high enough to shatter atomic nuclei, revealing their inner architecture. Cyclotrons and their later larger cousins, the synchrotrons and linear accelerators, became the most powerful looking glasses yet devised. Within their magnetic whirls, particles raced at speeds approaching that of light, smashing into targets and shattering nuclei into showers of fragments. Detectors, themselves marvels of engineering, recorded the fleeting traces of these collisions, curling tracks in cloud chambers, bursts of light in scintillation counters, and later digital footprints in vast arrays of silicon. The invention of the cloud chamber by Charles Wilson in 1911 added a new dimension to atomic observation. In this device, supersaturated vapor would condense into tiny droplets wherever a charged particle passed, leaving ghostly white trails that could be photographed and studied. The cloud chamber allowed physicists to see the invisible, to watch the dance of particles as they curved and spiraled through magnetic fields. Later, the bubble chamber, using superheated liquid instead of vapor, would capture even more detailed images, the tracks of particles resembling the looping signatures of living things. These chambers, with their quiet bubbling and drifting mists, were the canvases upon which the brushstrokes of the subatomic world were first recorded. Through them, new particles were discovered, the positron, the neutron, the muon, each a revelation, each a challenge to existing theories. Neutrons, in particular, proved to be a key that unlocked further secrets. James Chadwick's discovery of the neutron in 1932, using clever detection techniques involving beryllium and paraffin wax, completed the triad of atomic constituents. Neutrons, unburdened by electric charge, could slip into nuclei and rearrange their inner balances, sparking new forms of radioactivity and, under the right conditions, inducing the fission of heavy atoms. The tools of the atomic age were not limited to the laboratory. Nature herself provided laboratories on a cosmic scale, in the form of cosmic rays, high-energy particles from space that constantly bombard the Earth. These natural accelerators offered glimpses of processes too energetic to be replicated by human machines, and their study led to the discovery of still more exotic particles and interactions. Wherever new tools emerged, so too did new forms of measurement. The Geiger counter, for example, transformed the detection of radioactivity from a laborious counting of flashes into a matter of clicks and pulses, each a tiny echo of an atomic event. Scintillation counters, using crystals that flashed when struck by radiation, offered yet greater sensitivity. Film badges worn by scientists and workers provided silent testimony to the invisible dangers they faced. Yet the greatest revelations often came from the most unexpected quarters. In 1938, in a laboratory in Berlin, Otto Hahn and Fritz Strassmann, guided by the radiochemical expertise of Lise Meitner, stumbled upon a phenomenon both shocking and profound. When uranium nuclei were bombarded with neutrons, they did not merely absorb or rearrange, they split in two, releasing vast amounts of energy. The process, named fission, was explained by Meitner and her nephew Otto Frisch, drawing on the metaphor of a liquid drop stretched beyond its limits until it snapped. The discovery of fission was not just a scientific milestone, it marked the beginning of a new era, one in which the manipulation of nuclei would become both a source of power and a shadow of peril. The tools that revealed the atom's secrets became, in some cases, the very engines that harnessed them. To study the products of nuclear reactions, scientists developed ever more sophisticated instruments. Mass spectrometers, invented by Francis Aston, allowed for the precise measurement of atomic masses, confirming the existence of isotopes, atoms of the same element with different numbers of neutrons. The subtle differences in mass revealed the hidden architecture of nuclei and illuminated the processes by which elements are forged in stars. Spectroscopy, too, played its part. By analyzing the light emitted or absorbed by atoms and nuclei, researchers could infer their energy levels and internal structures. The patterns of spectral lines became a code, one that, when deciphered, told the story of nuclear transitions and decays. Behind these technical achievements stood the quiet, persistent work of calibration and innovation. Physicists learned to shield their instruments from stray radiation, to subtract background noise, to extract signal from chaos. They devised ingenious ways to trap and observe unstable isotopes, to measure the half-lives of nuclei that existed only for fractions of a second. As the tools grew in power and subtlety, so too did the theories that guided their use. Quantum mechanics, that strange and counterintuitive framework, provided the mathematical scaffolding for understanding the behavior of particles and nuclei. The Schrödinger equation and the Pauli exclusion principle became as essential as any glass lens or metal coil. And yet, for all the progress, each revelation seemed only to open new questions. The nucleus, once thought to be a simple cluster of protons and neutrons, revealed a teeming complexity: shell structures, magic numbers, collective vibrations, and the delicate balance of forces that held it together. The strong nuclear force, responsible for binding the nucleus, emerged as a fundamental actor, its nature probed by scattering experiments and theoretical models. In the great halls of research, vast collaborations formed. Teams of hundreds or thousands united in the quest to map the hidden territory of the nucleus. The instruments grew ever larger, the detectors more intricate, the data more abundant and complex. Yet, in the quiet moments, the spirit of the early pioneers persisted, a sense of wonder, a willingness to look and listen for the faintest hint of something new. Through the looking glass of the atomic age, we have seen worlds within worlds, each more strange and beautiful than the last. Our tools, tubes and chambers, counters and accelerators, are not merely instruments, but extensions of our curiosity, our longing to understand. As the night deepens and the mind drifts, consider the symphony of discovery that hums beneath the surface of things. The experiments continue, the questions remain, and the tools, old and new, stand ready in the gentle dark, waiting for the next spark of insight to illuminate the unseen. And so, with a sense of expectation, we move onward toward the boundless energies and puzzles that still lie ahead, just beyond the edge of knowing. What, in the end, does it mean to have found the fire at the heart of matter? The tale of nuclear energy is not merely an account of physics and engineering, not only a parade of discoveries and disasters. It is, at its core, a mirror in which humanity glimpses both its boundless promise and its abiding peril, an illumination that glows at the intersection of knowledge and wisdom, hope and apprehension. Let us wander now, not toward tidy closure, but into the wide, echoing spaces where questions dwell, and where the atomic fire casts its strange and shifting light. To peer into the nucleus is to look into a realm that is at once ancient and newborn. The protons and neutrons, bound tightly together by the strong nuclear force, are relics of the universe's first moments, forged in the primordial furnace mere minutes after the Big Bang. In every atom of calcium in our bones, in each speck of iron in our blood, resides the quiet testimony of cosmic violence and creation. Yet it is only within the last century that we have learned to tease apart these ancient bonds, to coax from them energy of a kind and magnitude undreamt by our ancestors. This is not the fire that warms the hearth or cooks the meal. This is the fire that powers the sun, the fire that shaped the elements themselves. Humanity's first encounters with nuclear energy were marked by wonder, fear, and a profound sense of responsibility. On the one hand, the splitting of the atom promised power that could lift nations, light cities, and fuel a new era of scientific achievement. On the other, it threatened destruction on a scale so vast as to seem almost mythic. Cities vaporized, shadows burned into stone, the very air poisoned by invisible fallout. These twin faces of nuclear energy, Promethean gift and Pandora's curse, haunt our collective imagination. What does it mean to hold such power? To answer, we must look beyond the mechanics of chain reactions and control rods, beyond the blue glow of Cherenkov radiation or the intricate loops of a fusion tokamak. We must reflect on the ways that nuclear energy has pressed us to confront our own nature, our aspirations, our hubris, our capacity for both creation and annihilation. There is a strange intimacy to the relationship between people and the atom. For most of history, the nucleus was a secret, its existence unsuspected by even the keenest philosophers. The atom, indivisible, eternal, a word derived from the Greek atomos, meaning uncuttable. Yet, the world inside the atom, once revealed, proved not to be solid or inert, but a storm of forces, a dance of particles, a place of hidden energies and probabilistic events. To know this is to realize that the universe is more subtle and intricate than our rough senses can perceive. The process of discovery was itself a kind of awakening. When Henri Becquerel noticed the mysterious fogging of his photographic plates, when Marie Curie isolated radium and polonium and watched their ghostly glow, when Ernest Rutherford fired alpha particles at gold foil and saw some rebounded as if by an invisible hand, each of these moments was a step deeper into the unknown. Each was a testament to the human drive to seek, to ask, to puzzle out the patterns behind appearances. But the awakening was not only intellectual, it was also moral. To split the atom is, in a very real sense, to alter the fate of the world. The mushroom clouds that rose over Hiroshima and Nagasaki were not just weapons, but symbols of the heights we might reach and the abysses into which we might fall. Never before had a single human decision possessed such immediate and far-reaching consequences for the planet as a whole. The atomic age, for all its technological marvels, is an era of existential awareness. We know now that we have the power to unmake as well as make, to darken the sky as well as light it, and so the story of nuclear energy is inseparable from the story of responsibility. In the flickering glow of the atomic fire, we are faced with questions that are as old as myth and as pressing as tomorrow's news. What should we do with power? How do we balance risk and reward? What is our duty to generations yet unborn, to the planet that shelters us, to the fragile web of life of which we are a part? Every reactor core, humming quietly behind its thick concrete walls, is a place where such questions find their concrete form. Engineers and technicians shepherd the controlled fission of uranium or plutonium, taming the chain reaction with careful design and constant vigilance. Policymakers and citizens debate the merits and dangers of nuclear energy, weighing the promise of carbon-free electricity against the spectre of accidents and waste. Scientists peer into the heart of the sun, seeking to master the still greater challenge of fusion, and ask themselves whether we are ready to wield such power wisely. Yet these are not only technical or political questions. They are, at bottom, philosophical. Nuclear energy reminds us that knowledge is not the same as wisdom, that understanding the laws of nature does not guarantee that we will use that knowledge for good. The atom, once split, cannot be unsplit. The shadow of Chernobyl, the silence of Fukushima, the lingering fears of proliferation and terrorism, all these are signs that the fire we have kindled is not easily extinguished. Still, to focus only on the dangers would be to miss another lesson, equally profound. For nuclear energy is also a story of hope, of perseverance, of the capacity to learn and adapt. The same creativity that made possible the bomb also created the means to harness fission for peaceful ends, to generate electricity, to power submarines that roam for months beneath the waves, to fuel spacecraft that journey to the edge of the solar system. The same scientific curiosity that unlocked the secrets of uranium and thorium now drives us to explore new frontiers. Thorium reactors with less waste, fusion devices that might one day provide clean energy for all, medical isotopes that diagnose and treat illness, radiotherapy that saves lives. There is in the quiet hum of a nuclear plant something that speaks to our deepest yearnings. The dream of abundance, the dream that energy might flow in endless streams, that want and scarcity might be banished, that the night might be lit not by firewood or oil or coal, but by the very processes that power the stars. It is a dream as old as civilization itself, a longing for freedom from the hard constraints of nature. In the controlled fission of the atom, we glimpse a future that might be, if we are wise, a future of light rather than flame. Yet the mysteries endure. Even now, a century after Rutherford first probed the nucleus, we do not fully understand the forces that hold it together, nor the full spectrum of possibilities and dangers it presents. The strong nuclear force, the glue that binds protons and neutrons, is described by quantum chromodynamics, a theory as complex and subtle as the nucleus itself. Why does the universe prefer matter to antimatter? Why do some isotopes linger for billions of years, while others vanish in an instant? Why, in an ocean of possible reactions, do only a handful occur within the stars, forging the elements upon which life depends? Each answer opens new questions. Each discovery reveals fresh enigmas. There is, too, the mystery of our own relationship to this power. Why did it fall to us, creatures of flesh and bone, to unlock the heart of the atom? What does it mean that in the depths of our ingenuity we have found a way to shape the destiny of the planet for good or ill? Is this a sign of our maturity as a species, or a warning of our hubris? Can we, in the end, be trusted with the fire of creation? To reflect on these questions is to recognize that the story of nuclear energy is not finished. The reactors of today, with their domed containment vessels and intricate safety systems, are but one chapter in a longer tale. Fusion may one day render fission obsolete, or new discoveries may upend our understanding altogether. Or perhaps we will choose another path, turning from the atom's fire to the wind and sun and water, seeking harmony with the earth rather than mastery over it. In every case, the choices we make will be shaped by our values, our fears, our dreams. But perhaps the deepest reflection is this, that to know the atom is to know ourselves. The nucleus, with its tightly bound core and restless energy, is not so different from the human soul, capable of both tremendous creation and sudden, catastrophic release. We too are creatures of contradiction, driven by curiosity and fear, by hope and caution. The story of nuclear energy is, in the widest sense, a story about the human condition, a tale of what we might become and of the dangers that attend our most daring ambitions. And so, as the night deepens and the world quiets, the questions linger. What kind of world do we wish to build with the fire at our fingertips? How do we balance the gifts of Prometheus with the warnings of Pandora? What does it mean to be stewards of such power, and what kind of wisdom must we cultivate to use it well? In the deep silence of a reactor at rest, in the faint traces left by cosmic rays in the atmosphere, in the patient labor of scientists and engineers who seek to understand and harness the atom's gifts, there is a sense of the unfinished, a sense that the journey continues. The mysteries of nuclear energy are not only technical puzzles to be solved, but invitations to reflection, to humility, to awe. The enduring power of the atomic fire is not simply in its capacity to light cities or level mountains, but in its ability to make us ask, who are we that we possess such knowledge? What will we do now that we have tasted the energy that binds the stars? The answers are not given, but must be sought again and again in each generation. And as the world turns beneath the silent stars, those vast, distant furnaces whose fires mirror the ones we have kindled here on earth, the questions remain, waiting for the dawn. For in the heart of the atom, as in the heart of humanity, the story is never truly complete. There is always more to seek, more to wonder, more to learn. As our journey through the heart of atoms gently drifts to a close, we watch their tiny worlds dance like comet tails fading into the hush of space. May this quiet wonder of splitting and fusing linger softly in your thoughts, inviting peaceful dreams beneath a starlit sky. Return soon, dear dreamer, for more cosmic tales that await in the quiet folds of night.